you know all there is that's important about cycloplasticity and constitutive equations. I'm sure all of you could solve my one-page slide on plasticity and write an algorithm that would give those nice, beautiful pictures, but it might take a while. So I want to go on now to the strain-based models, and there are several of them that I will talk about. And first model I want to talk about is the idea of work and plastic strains. And it's not a surprise that the easiest thing to try if you want to work in multi-axial fatigue from the strain basis is just a literal extension of the uniaxial approach. The uniaxial approach would say, fine, we just use the principal strain. And if I want to do that for something in torsion, let's say, well, of course, we know that deformation is driven by shear, so instead of using the principal strain, we could use the octahedral strain, right, calculated just like the octahedral stress. And what you see is that people who try these kinds of things get data that looks like this, apply the octahedral plastic strain and the cycles to failure, and in fact you find the tension data here and the torsion data here, and this difference is about a factor of 2 in strain. And of course, because of what we've been doing for the last day or so, then you have some understanding of that. Of course, we know it's because of the growth of microcracks, and it's harder to grow a microcrack in torsion, and so we expect always for the same strain the torsion test to last a little bit longer. And then there's a whole group of models like that. And there's another whole group of models that model the plastic work. And these are people that do things like calculate the energy. A bunch of energy models. And if you think about it, that's kind of attractive, right? So you get these really complicated hysteresis loops, right? So I'll draw a simple one, but I can look at the axial stress and axial strain. And I can look at the shear stress and shear strain, whatever it looks like, and just take the energy in here and add it to the energy in here and calculate the fatigue damage. And I can do that for as complicated a loop as I like. If I go back a few slides, right, for that funny history, this has several cycles, so it has the isotropic hardening in it. But if I looked at the basic loop here, it goes up here, down a little bit, up here, down here, up a little bit, and back. I could just calculate the area in here and calculate the area in here and add it together. So it's a really convenient thing to do. And there are a whole lot of people who do that. And a lot of papers that have been published. And you get data that's like this. And so these are doing things in different phases. And so instead of taking this bar and pulling on it and then twisting it, I could pull on it, and then as I begin to twist it, then I could unload in the other direction, such that when I have the maximum torque on, I have 0 axial strain, and when I have the axial strain on, then I have 0 torsional strain, and just all kinds of funny paths. And that's in fact what these are, just different phase angles between the tension and torsion. And if you look at all of the data, then what I have found is that all the data, of course, scatters between the axial results and the pure torsion results. And of course, it scatters by about this factor of 2. Right? So and then people do things which are really strange. They say, well, okay, I make this observation, and so torsional work is only half as damaging as tension work. And of course, you can collapse all that data. Right? All that data. Right? Absolutely wrong. Absolutely wrong. I always like to show that with a little bit of an experiment. So I need to make my test specimen. So I'm now in the machine shop making my test specimen. So I now have it. Right? Pretty good test specimen. So you realize what I did is that I have a test specimen, and you can see that there's the little microcrack. So I not only made a test specimen, but I also made a very good microscope so you can see what actually happens. Right, so you see that. And so let's just think about what this means to use work or any energy base. So let's put in a lot of energy. Wake up. So I'm putting a lot of energy into this, right? Absolutely nothing happens, right? Well, let's put a little energy. Oops. How can energy ever work? Because we know the fundamental physics is there's lots of little cracks in there, and little cracks are planar in nature in certain directions. So the energy models are doomed from the first physics. They are just doomed to failure. So energy models are usually proposed by people who've not been in the lab to see what happens. And these are people who only like to do calculations. But energy models, right, just don't work. They don't work very well. And they never will. Fatigue cannot possibly be a scalar parameter. But all energy is, and that's what they're attracted to, right? So I get an argument at some of the conferences with them, and I stood up at a conference and I did this one time. The guy was making his presentation. I said, this can't be right, and so on and so forth. And then he says, oh, I'm calculating a different kind of energy. And I just sat down. I mean, I guess there is different energy, the dark force. I don't know. So I never talk more about it than that.
I like to do things which are more reasonable and actually used.
And, you know, when you look at the strain approach, probably the most famous are the work of Brown and Miller. And what they did was they went and they looked at literature that was available and summarized all of it. And they concluded that you could never correlate the fatigue behavior with only one parameter. Well, we already know that because we already saw the kinds of ideas from Finley, right, that you have to worry about this idea of a sliding crack and an opening crack. And what Brown and Miller did is they then did some experiments. And so if I look at this bar, then I can do a test with the same shear strain, and I can do that test in tension, torsion, and any combination of tension and torsion, just by varying the ratio of axial loads and shear loads, right? But I can vary the ratio in such a way that the shear strain itself is always constant. And like I say, I can get the same shear strain either by twisting it, pulling it, or any combination. That's exactly what they did. And so this is some of their data. And this is a constant shear strain of 0.003. And this is the normal strain amplitude. And the normal strain is, okay, I have the shear strain acting on some plane of the material, and I have the normal strain transverse to that. Well, they're having fun. Probably more fun than we are. I don't know, we have some children that come to our house every day. They have been coming to our house, I don't know, the last 4 or 5 years. One of them is now 5 and the other one is 4. I like them very much. I stay home and play with them before I go to the office. Yeah. And I like it because there are always things out of place in our house. So when I leave my jacket someplace, it doesn't look out of place. You know, just with all the other kids. And they're very much fun. They're very much fun. And of course, in their eyes, I am functionally illiterate because I don't know all of the television characters. So I have trouble talking with them, but other than that. So I enjoy it. It's fun. Okay, so back to our science. So what I can do is I can do a test in pure torsion. Of course, there's no normal strain. You get from Mohr circle in a lifetime maybe here. And as I increase the amount of the normal strain, and so we would interpret it, okay, I'm sliding like this, but then I'm opening like this, and so as I increase this opening strain, then the life decreases, and so here's their data. And then after they do this, then they have to propose some model, and they have a couple of different kinds of strain, and that you realize I could have the same shear strain with 2 different load cases. And so here's a cube of the material, and I could think about developing a particular shear strain such that that shear strain tends to drive a crack along the surface. And that's what happens when you load something in torsion. Or I could have another scenario where I have this case B, and that drives a crack in shear through the thickness, and this is what happens in biaxial tension. And so they make a distinction about what kind of shear strain they have. And this is what they wrote. I highly recommend that when you reference something that you actually read the paper. I know that's a unique concept. Rather than give historical credit, because usually the authors have a lot of good things to say which are lost because people pick just the part they want out of the paper. Even if it's the wrong part or an insignificant part where the author says, I tried this but it didn't work, somebody may reference that they tried it. You know, so you've got to be careful. Anyway, here's what they actually wrote. They said, being a slip process, the initiation mechanism will be controlled by shear strain. So Keith Miller does believe in crack initiation. He wrote it.
Yeah.
Secondary effect will be the tensile strain across the maximum shear plane, which influences dislocation mobility and the decohesion associated with the slip process. Most metallurgists would not agree with that. They don't believe that the tensile strain has anything to do with dislocation mobility. Right? But that's what they want. Furthermore, a law involving a combination of maximum shear strain and tensile strain will assist in the correlation of crack growth by cleavage and brittle materials, because cleavage will be controlled by the maximum principal strain. Thus, considering both, you can correlate the behavior of all materials. So it says somehow we need shear strain and we need normal strains. Essentially, that's their rationale for needing. And so then they presented their data in what they called sigma plots. Now, how many have seen a sigma plot? Good, no one. Yeah, this was a strange idea. They tried to revolutionize the way people looked at fatigue data. Not surprisingly, they were not successful, other than in a few of their own early papers. This is the normal strain, this is the shear strain, and these are constant life contours. And this contour represents uniaxial straining, so any point along here. This was equal biaxial straining, any line along there, and this was pure torsion along there, such that here are all the combinations of normal strain and shear strain that would give you a life of 1,000 cycles and a life of 10,000 cycles. And they spent a few years promoting this, and of course, everyone else ignored them. That's also a good lesson. If you want to do something, you have to cast it in a framework that people are ready to accept. If you cast it in a strange framework, you have a lot of work to do, a lot of extra work to do. All right? So, basis of their theory is that both shear and normal strain were important. And it didn't take very long before they changed their theory a little bit. And they changed their theory to look like all other fatigue theories. And they said that there's an equivalent shear strain, and the equivalent shear strain is a function of the maximum shear strain range and the normal strain range, and two different factors here. Right? I've also never understood why they did this. You know, normally when somebody makes a proposal and they write their first paper, they have a first order model. And then when they need a second paper to go to a nice conference, then they have a second order model. Right? They started off with the second order model. Now, first of all, just the model. What do you suppose a really good value for alpha is? Fits almost all the data. 1. But you know, you might as well write it. It looks more glamorous, I guess. More elegant. Yeah, but 1 fits all the data. So no one I know has ever used this form. Right? No one ever used that form. Right? How about the value of S? What's a really good value of S? 1. 1. Works really, really well. You know, if I have all the data, I can fine-tune that constant, but most people never have all the data. We always use 1. Yeah, it works. It's a pretty robust constant and so on. But, okay, the model is there. So someone else can't propose an improvement. You know? Well, it would have been an easy master's thesis for somebody to propose this small improvement. Okay, fine. So that's their idea. Let's just think about what it means, though, right? Right? So both parameters. Then they add them together, not unlike Finley's, right? We think about what Finley's idea is, and we can make the same hand-waving arguments about the growth of microcracks. And that's a driving force, and then there's a modification for the normal strain, and then there's some material sensitivity that you can introduce. And if you look at this, then we draw Moore's circle for it. then in Moore's circle for both the shear strain and normal strain, then what you find is given some applied strains, epsilon x and gamma xy, then here's what the maximum shear strain will be here. But of course, there will be another maximum shear strain 90 degrees apart, and that will be here. So one of the unintended consequences of Brown and Miller's model, which they never actually discussed, is that cracks should always form two sets on 90-degree planes. How many times have you seen cracks on two sets of 90-degree planes on something that's broken? But that's fundamentally what their model said. There should always be cracks on two planes 90 degrees apart because both of them are identical. Both of them are identical. So that's an inconvenient fact that they gloss over a little bit in it. And then to make it look like all other fatigue data, right, that's what their formula is, then they write it to look just like strain life data, and so you have a few extra constants. You will recognize these are the traditional strain life constants here, and epsilon f prime, and then slopes b and c, and so forth. These constants A and B are not adjustable constants. They are constants which just involve Poisson's ratio, and Poisson's ratio for the elastic Poisson's ratio of 0.3 and plastic Poisson's ratio of 0.5 make these constants slightly different so that you can use the shear strain here. I think this one's 1.5 and that one's 1.3, but I'm not sure of the magnitude. But I think that's what they are. And so that works pretty good. And of course, this is, I'm working in this area and it works, but how could I do my own research if I just accepted this? And in fact, I looked at it through very different eyes because this was troubling. That you'd have two 90-degree cracks because I didn't see that. I only saw one. You test something and I pull and twist on this tube, there's a crack in a particular direction. Brown and Miller's idea said there should always be these two 90-degree cracks that form. What does it say? What do I want? Just escape? Escape. Okay. Another problem with this conception, what they said was, on the plane of maximum shear strength, calculate the normal strain. That has to be a big mistake. Can't possibly work. How do I say that? Right? Look, let's just do a little thought experiment. I put a big tension cycle on here. And of course, that will put a big shear strain on a plane 45 degrees like this, right? And now, I follow this by loading only in torsion. The plane of maximum shear strain is not the plane of failure. It's all these torsional strains at a lower strain. And so there's a whole class of models who make this statement first. On the plane of maximum shear strain, or shear stress for the stress models. It doesn't matter. It doesn't matter. The damage model itself ought to tell us where cracks form and how they grow. So I set off to show what that plane should be, and it's because of my background. So I was one of the PhD students of Morrow. There's a picture of him when he retired. Pretty interesting guy. He retired, and when he retired, on the day he retired, he did not come back to the university. At all. No. Completely finished. He wasn't sensible like me. I told you, I retired 8 years ago, and I still go in almost every day. So, right? Yeah, there he is. He moved from Illinois, which is farm country, and he moved to Ajo, Arizona, which was out in the middle of the desert. In the middle of the desert, I'll show you Ajo. Right? So, if you go to Phoenix, middle of Arizona, there's Phoenix. You drive for 2 hours out into the desert. There's absolutely nothing but desert. And then you make a left-hand turn, and you drive 2 hours, and you arrive at Ajo. And when you arrive at Ajo, then Ajo looks like this. This is a huge copper mine. And this is what's left, and this is the town of Ajo. And when Professor Morrow moved there, they had just closed the mine. And so the town had 10,000 people, and its population dropped to 2,000 people. And he looked at this, and he told me, he says, oh, this is good. This is a good opportunity to buy land. So he bought a lot of land in Ajo, Arizona. He's the major landowner of Ajo, Arizona, right? In it. So I'll tell you the other why. So some people just have insight. They just have insight. And so with the Ajo story, the population of Ajo is now back to 10,000. And Professor Morrow doesn't own very much land, but was able to sell at a very good profit. Because he had insight that people would want to retire to Arizona, but they don't want to live in the big city of Phoenix. They want to go in these small places. Just insight. Yeah, this is the school. So Professor Morrow is still teaching, right? But yeah, this is the school, and so he goes in and makes paper mache things with the kids and so on. I want to tell you about insight. So I mentioned yesterday the PDP-11 computers, the first computers we had in the lab like this and like this and like this and so on. And he was not computer literate, but he kept asking, how does this work? And of course we tell him things about material and so on. And he says, no, take this apart. Show me, what is the part that makes this work? And so, okay, we have to take this apart. What choice do we have, right? He's the professor. We have to do what he says. So we go in and, who makes that? And so, oh, these are some Intel chips. So he also bought a lot of Intel stock at the first opportunity to buy Intel stock. Because he said, this will be transformative. This will be transformative. And yeah, so, well, of course, in both of them, he, of course, makes a lot of money. So it's just insight. And he had the same insight, of course, when it came to fatigue. And that's why I tell this funny little story. Yeah, that was... And this is his classic paper. This paper is cited with all the people that have energy models. And when he started off with his fatigue theories, he also used hysteresis energy. And he told me, he said, yes, I started this and I formulated this with energy. But he went out to the industrial people, and in Illinois we are about 100 kilometers away from the Caterpillar Technical Center, and about 200 kilometers away from the John Deere Technical Center. And so we get a lot of research work from them. And he said, I would go out and I would talk about the theories and so on, and bosses there, and ask for money, of course. And the bosses there would say, I don't know anything about this energy, but we measure strains in the field and we calculate stresses. Don't tell me about energy. And so he completely changed his ideas by listening to these people that kept saying, we calculate stresses and we measure strains in the field. And so he got rid of all the energy concepts. But everybody cites this paper in 1965 because the energy should be the right thing, because that was his first paper he could never sell. But when you dig down in it and read it, right, this is the most important thing from the entire paper. What it says is, look, we understand that the cyclic plastic strain is related to dislocations, right? But stress is really related to their resistance. So if I think about a model, a stress-based model probably is not right. Neither is a strain-based model alone. Because think about this. If I need to deform something, I could strain a rubber band, very large strains forever. And the reason I can do that is the rubber band puts up no resistance to the deformation. Absolutely not. On the other hand, I could have something that's very strong, and as soon as I start to deform it, it builds up very, very high stresses. So somehow you need to have this concept of both stress and strain being important in the process. But it's not the energy, right? But you need both stress and strain. And we can think about that, right? Here's a little picture of a dislocation. And the reason that energy is not good is that we look at this dislocation, and I put a shear stress on that, and to move this dislocation, there's some notional force that resists that. And so you can see that as I shear this, this force resists the motion of this dislocation. But if I shear this in the opposite direction, nothing happens. Like this dislocation can't. And that's the theory behind that, behind the models. And so, of course, you know, this is how I was trained. That the stresses must be important. They just must be important. So I thought about this and said, gee, you know, I could devise a simple set of experiments to show that Brown and Miller's ideas, while conceptually they're right about the importance of shear and normal strain, it's really the stresses. And so I devised 6 different loading histories to try. And these different loading histories, here's the axial strain and shear strain, and so this is just a test where I pull and twist. And I always keep the same range, like that. And you can see the only thing that's happening is I'm shifting around the mean, and that shifting around the mean will shift around all the different stresses that are there. Right? So if I look at these, then I can say, well, okay, I have a particular life here, of course. I can choose what that is depending on what the load levels are. But let's just accept this as the baseline. And what happens if I move only in one direction, like this? Same range, you can see I just shifted that. So what will happen to the life? Longer, shorter, about the same. So what's the effect on fatigue life of a tension mean stress? Longer, shorter, about the same. Shorter, right? Sure. We all know about the Goodman diagram from 1890, and so yeah, sure, that should be shorter. And how much shorter, of course, will be determined by how much the mean stress is, and so on. Fine. How about this one? We put it all in compression. Longer, shorter, about the same. Students delighted in bringing me the test results since they never matched my preconceived ideas. Actually, this one turns out to be about the same as this one, even though the stresses are in compression. In a few minutes, I will explain why. So then I thought about this one. Well, you know, mean shear is not particularly damaging, and so I have this one cycling back and forth in tension, and I'm just going to introduce a mean shear strain, so that should not be particularly damaging, I thought. It turns out that life is lower. And these two really fooled me, right? Here was my thought experiment. Right? Because I never believed in going into the lab to just do experiments unless I had a particular outcome I thought was right. Yeah, I don't think you learn much, right? You need to do critical experiments and say, if my thoughts are correct, the experiment should turn out one way. If my thoughts are not correct, it should turn out some other way. I think the worst thing to do is to just dream up a bunch of random load paths and then try to explain it afterwards. I think you get nowhere that way. That's, as I mentioned earlier, the spreadsheet mentality. And here was my thinking. Look, we shear this, right? And while I have the maximum shear, I also have the maximum opening in tension. And that should be pretty damaging. This one. Right? Let's do the opposite one. I'm shearing this, but at the moment I have the maximum shear strain, I have compression. And I have these models in my mind, right, about sliding and all these nice pictures about fracture surfaces and the surfaces sliding past one another and debris and so on. That should be a really long life. And so I thought this one should have a really long fatigue life. Because when at the moment I have the maximum shear strain, I also am pressing it together, right? And so the students came back to me and the life was about the same. And so, since I have spent my career a lot of time in the lab, I never believe one test result. Never. Right? One test result doesn't alter my view of the world, and that's because I know how easy it is to get the wrong specimen, how easy it is to turn the knob so that it's the wrong load, all kinds of things that can happen, and so on. So if somebody brings me a result like that, of course I criticize the experiment and send them back to do it again. And this time to be really careful and don't make the same mistake. So you can imagine what happens a few days later. The student comes back and said, "Oh no, professor, results the same. Something's wrong with your theory, you know. What am I going to do?" This is what I thought, right? So, yeah. And you know, these happened when I was a young professor, so the consequences of failure were more drastic than they would be today. And then, of course, we have this one. Of course, we put a big mean tension. This one should be a pretty short life. Finally, I got another one right, and so on. So something was clearly wrong with all that. But when I mentioned the other two, they're out of the lifetimes from a couple of it. It's pretty hard to argue that those are not the same. That those are not the same. Okay, so something is wrong. What's wrong? And what I learned from these two experiments actually set the path of what I thought in multiaxial fatigue probably for about 10 years. And what I never understood was I didn't understand the criticism of the Brown and Miller model about two different shear planes. Look. These are those two sets of planes. And so if you load something in tension and torsion, there are two 90-degree shear planes. Right? Each one of those will have different stresses. And these are the stresses on those two shear planes. If you load on equal amounts of strain and tension and torsion, that plane turns out to be 20 degrees this way or minus 70 degrees that way. Those are the two shear planes. And these are the stresses on one of them. Right? And these are the stresses on the other. Well, you can see what happens. First of all, the stresses here on the minus 70-degree plane are really, really high. Right? They're also high on the 20-degree plane. And look what happens down here on the other one. This stress, right, still high. And this one is almost zero. They're very different. Right? Which of the two planes is it going to fail on? This one's going to pick this one. This one's going to pick that one. That's the difference. Two shear planes will have very different stresses. And when I did that, I found that when I looked at the different testing, and I looked where I actually found cracks and plotted that versus the maximum stress, the cracks always happen on the one of the two planes that have the maximum stress. And what happened was I could never in my mind predict what the stresses were. Never. I could say, here are the external loads and pull and twist and so on, but I could never, in my mind, predict what the ultimate stresses would be. As soon as I did all this plasticity modeling, so that I could calculate the stresses, then it was just clear. But only through the calculation of the stresses, because none of us can think in terms of those differential equations for the plasticity models. And so this convinced me that the stresses were, in fact, the most important thing, not the strains for the normal stress. And here you can see all those cracks. As I mentioned to you, all those cracks go like that. You find a single crack here, you don't see anything there, and so on. Right? So what's really important is maybe shear strains acting on this plane, and whatever kind of stresses try to open it. But it's the real stress on one of the two shear planes. Okay, so that's what you get. By the way, this one I showed you yesterday, now I can tell you that these actually are the stresses that act across the shear plane. Shear stress is the same for every one of these, and you can see when the shear stress is not very high, or when the normal stress is not very high, the life is a long time. And the reason the life is a long time is because it inhibits the growth of the microcracks. If I define crack nucleation about 10 microns, way down here someplace, that happens almost immediately in the lifetime, and there's almost no effect of this normal stress because it's down shearing, right? But as soon as the crack builds up a little bit of length, this normal stress either opens or closes that crack, and if there's not much normal stress, it grows very, very slowly. So I'd like to use that idea and give you another quiz. I like giving these quizzes. Right? If that's a good view, of this process, let's look at this experiment. Let's take a tube and just cycle it in axial loading, and we will cycle this with some mean stress. Okay? And we, of course, know what the lifetime will be. We know, compared to just cycling this with zero mean stress, that the addition of this tension mean stress will be detrimental. And we know, of course, that if we test this, that cracks will nucleate on shear planes here, and they'll grow on shear planes, and ultimately they'll turn into principal stress. Right? We know that's what will happen. What would happen if I did a little bit different test? What would happen if I took this strain range and applied it without a mean stress? But I pressurized the tube on the inside with the same mean stress that I had here. Okay? You can imagine the experiment. You can imagine I like this experiment a lot when I propose it, because now I could build a new test machine to do pressure. Write a nice proposal, get a grant, wait a year, thereabouts, buy some nice equipment. Okay, now we're ready to run an experiment. But the reason I got the equipment is I had a critical experiment because I predicted all the results first. And so now we need to confirm that, right? So what do you think about the lifetime of these two tests? Same, different? So let me ask a little bit different question, right? What is the basis for making a decision if they're the same or different? So basis for decision must be, I have some model in mind, right? And so the model we are building up is we have this model, at least conceptually in our mind, that okay, we're going to have shear back and forth like this, right? And we know that as we have shear back and forth like this, that any stress which tends to open that shear crack will be more detrimental, right? That's our physics model that we have behind the scenes that's guiding it. Right? So if these two have the same stresses, right, then the lifetime will be the same. And if they're different, the lifetime will be different. Right? So do these two loads produce the same stresses? So, well, we can look at that. Okay, so I make a box instead of a cube. That's the critical place on the surface, and I think about, okay, with microcracks, so there's a potential shear plane that looks like this, and so this is the first case, right? And I'm going to load this in this direction. In this direction, I will have some strain delta epsilon, and I'll have some mean stress sigma 0. And if I look at this strain delta epsilon, then this will produce a shear strain that exists on this plane like this. Right? And it will also produce a shear strain on this plane that looks like this. Right? Both of those two 90-degree planes. And then there will be a mean stress, and so this mean stress exists in this direction, right? And that mean stress will resolve into a stress here of the mean stress divided by 2, right, on that plane. And it will also resolve into the same mean stress, sigma 0 over 2, on that plane. Right? So that's the state of stress and where all the action will be. Let's look at the one on the right. So again, now we have the axial strain here, just as before. So of course, these are the potential failure planes. Like that. And now, we put the mean stress there. Same magnitude as this one. And what's going to happen? Right? This is going to resolve into a stress on this plane of sigma 0 over 2, and it's going to resolve on a stress on this plane of sigma 0 over 2, right? For Mohr circle. Right? And you can see that these are identical. Right? The little material element where failure is going to occur doesn't know the difference in these two loadings. Doesn't know the difference at all. If the material element doesn't know the difference, right, same stress state, then they should be the same life. Right? Right? Pretty critical experiment, isn't it, whether you've got the right idea? Because you don't need to have a plot, you don't need to show how close the lines come to the curve. These two either have the same life or they don't. The same or they don't. So how about the experiments? So here are the experiments. So here are strain range, mean stress. Right, we'll look at the top row first. This is what happens to the one on the left. This is what happens to the one on the left plus the mean stress that's there. I claim these are the same. Right? Certainly not much difference. And this is what would happen if I only had R equals 0, and that is I took off this mean stress and just ran a test with that strain. Oh, that's pretty good. Right? I like this result. Right? Yeah, you know, sometimes you should quit while you're ahead. So then I reduce the levels in half. Okay? And I put a really high mean stress. And look what happened. Okay, this is what happened for the one on the left. This is what happened to the one on the right. Very different. Very different. So something's wrong again. Something is wrong again. Because I thought, you know, this one, these should have been the same as these, right? And instead, these are much more like these. Right? Much more like no effect. How could that be? Stresses are the same. Yes?
Don't we have in the second case, don't we have circumferential stress, which means it acts in plane with the crack?
Yes.
Since it's a tube, since it's a hollow tube, so if we put a pressure inside, isn't the stress which is applied to the material, onto the thickness, it's in plane with
yeah, through the thick, the stresses, though, are very small.
yeah.
We make a thin wall,
So
too.
basically we don't have the crack open, we have just fine.
Yeah, it does have to do with the cracking, right? But not the in plane. Look, here's what happens. Right? I mean, you are right. Look, at the beginning of the test, right, the crack grows more or less in shear. Okay? After a little while, the crack turns to grow in tension. Let's look at what happens in tension now. So same two cases. Right? And I'm going to load this the same delta E and of course the same sigma 0. And now, if I consider what happens in tension, I have this plane, right? And this plane sees a delta E and a sigma 0. How about this one? It certainly sees the delta E, right? Yeah, but sigma 0 is over here. No effect. No effect. That's exactly what you see in the picture. This is this idea that there can't be a universal theory because materials will do what they do, and cracks turn from these shear cracks, and they grow into tension when they get bigger. And you can see this happened after it got to be about 1 millimeter. Right? And it can hang on for a while as it's growing like this. And of course, when this is growing like this with this mode 1 crack at the end, nothing happens. Nothing happens. So again, there's not a good universal model, right? Because the failure modes change. So you know, when I actually analyze things, I actually analyze both possibilities. I always say, I'm not sure if it'll grow in mode 2 and shear or in mode 1 in tension. I analyze both of them. And then I decide if I want to be an optimist or a pessimist, which number I choose. But you know, the problem is, yeah. Well, remember when I started out, there was no good model when I talked about the physics, right? But as soon as I show you what the physics is, right, it's very easy for us to explain and understand what happens and why it happens. So in the end, this is the model. This is the model that I came up with, and so that was my idea. I'll tell you a little bit. Most people think that Fatemi was my graduate student, and that's not true. In fact, he didn't even go to the same university. He went to the University of Iowa, and interesting story. I met him at a technical meeting, and he was a graduate student, you know, beginning PhD student, and he was talking to me, and he said, "Oh, I have these interesting experiments I would like to do, but I can't do them at the University of Iowa." He said, "We have a test machine, but it's in a different lab, and the other professor won't let me use it." Okay, we know that happens, right? Universities are not really there to disseminate knowledge. Sometimes they're there to build up empires, and so I can't let someone from the outside into my empire. I think that's crazy, but that happens at universities. I'm sure it doesn't happen anywhere else, but it's certainly a university. A few of you are shaking your heads, yes, must have run into this problem. Anyway, so he's explaining this to me, and I said, "Boy, those are very interesting experiments." And I said, "Why don't you just come and run them in my lab?" You know, I thought about this as, you know, here's the chance to do some interesting experiments, and someone else is paying for it, you know, because his advisor at the University of Iowa is paying his salary, and I got to direct the work. I mean, what have I got to lose? So he came and did very nice work. You know, he was very prepared and came and, you know, worked very hard and so on. And I went back, and he came to see me one day, and he has a model which will fit all of the data. And I took one look at this model, and I just said, "It can't work." So you can imagine how devastating that might be to a young PhD student. You know, after all this work and preparing charts and so on, I just can't work. It can't work. And in fact, none of these models can work. And what happened was, I mentioned a few times that, you know, even to this day, when I want to try something out, I build my own computer code models and so on and just try them out. And I tried something funny. I had my latest and greatest calculation code, and I tried to calculate the fatigue life for a tension test, just for fun. Now, of course, in a tension test, the calculation should calculate that there's no fatigue life. Right? But my code gave me an answer. I said, "Well, that's strange. That's strange. It's a tension test, right? I just have a static hold in a tension test. How can that be calculating fatigue life?" Thought about this a while and thought about it, and then it just dawned on me. Let's just look at Finley's model as an example, right? There's the shear stress plus, that's the parameter, right? Suppose the shear stress were 0 and the normal stress were high. What would the value of that parameter be? If the shear stress were 0 and the normal stress were high. Might be some high value, right? Of course, right? So that means there must be fatigue damage under a static stress. That's what the model says, mathematically, right? there must be fatigue damage even under some static stress. And of course, that's silly. Of course, that's silly. And so it made me think about the structure of the models. So all these models really have a fundamental flaw, right? Fundamental flaw, and it goes back to the statement I had at the beginning of this on the plane of maximum whatever. You see? It's just a problem. It's just a problem. And Fatemi had a model that looked kind of like that. And I immediately recognized it and said, oh no, oh no. Look, you have to be sure that if there's no shear stress or shear strain, there's no damage. I said, that's what the structure of the model looks like. And so I sat down at my desk and said, okay, just take this, right? So start with the shear strain and multiply it by the normal strain. And so if you multiply it, or the normal stress, I said, if you multiply it, well, of course, that gives you energy, and that's not right. And I said, oh, just do this. Just multiply it by that. And then he said, oh, it's got the wrong units. He said, let's just normalize this by dividing this by the yield strength. And I said, okay, that looks pretty good, go try it. Probably all of a 10-minute discussion. Yeah, that's how the parameter actually came about. But it was this idea about just checking the structure of the model, and that's really the lesson I want to leave you with, right? See if it does reasonable things just in its formulation. Like I say, this is pretty fundamental, that this could be a big number, right, and give you fatigue damage for a static test, right? So think about what the model looks like in these strange cases, right? Not the curve fitting afterwards. All right, so that was the idea, and then of course you put it into this math and so on. They also convinced me. He said, "Oh, we need an adjustable constant here so we can make the curves look a little bit better." I always use a constant K of 0.3, and it works pretty good. So I never deal with calculating it. You can write it in terms of shear or tension. Right? Right. You got to be a little bit careful though in all of these. As what I alluded to before, not all materials nucleate microcracks and grow these microcracks in shear. This is what happens to stainless steel. And so here are 4 different loading paths, and again, this is tension strain in this direction, shear strain in this direction. Here's these out of phase paths, and here's a box, and here's that. And what you see is that stainless steel, right, one of the most ductile materials we have, actually fails because of the growth of cracks on principal stress directions. So if we think about the growth of principal stress directions, and that's where cracks initially form, once a crack forms, it always tends to grow perpendicular to the applied tension load in these kind of tubular specimens, and that's what you see here. Crack initially forms here, and then after it starts to grow a bit, then it turns and tries to grow in the principal stress direction or strain direction like that. So we go back to my previous chart, right, like that. We make all these arguments about shear. They have to be completely wrong in this material. Okay. Because our ideas was that the lifetime is governed by shear stresses and normal stresses. So you always have to consider the possibility that there are some materials for which we are interested in the principal strain direction. Microcracks grow, but they grow in principal strain directions. So we need a model for that. And it would be tempting to develop a new model and put my name on it. Maybe I could become famous that way. Probably not. Probably not. Or I could just use the existing models in the literature. Right? By this time I already had tenure and was already established, so I had no need to put my name on things, and so I looked at the Smith-Watson Topper. That's the usual model for mean stresses in uniaxial loading, and it turns out to work. It turns out to work very well. And so there are situations for which we are interested in the growth of microcracks in mode 1, and the driving force becomes the stresses opening those microcracks, but instead of opening the microcracks on the shear planes, they are opening the microcracks on principal strain planes. And then, of course, the strain range is what drives that. And you can write that out, and that's what the theories look like.